Somebody can check in the YouTube. Yeah, one can start now, I think.
Yeah, Priya, over to you.
No, but first to check once it is in the
yeah,
YouTube.
it is there in YouTube. Yeah, it's working.
You can start.
Yeah, YouTube is working.
Yeah, Priya, you can start.
So good afternoon. Welcome everyone. Thanks for joining us today in this event of Curry Leaf. Curry Leaf is a math club of MTTS alumni. Our aim is to bring together the participants of MTTS program on a single platform and organize several events related to mathematics for the wider mathematical community. Curry Leaf started in the year 2020 and we have organized several interesting events so far. We welcome you to have a look at our website. You can find the link in the chat box. We will have a series of 4 lectures by Professor Diganta Borah starting today. Professor Borah is an associate professor at IISER Pune. He did his PhD from Indian Institute of Science, Bangalore. Professor Borah is also an alumnus of MTTS. Professor Borah will be speaking on Riemann mapping theorem via the Dirichlet problem in this lecture series. We have been thinking of organizing this event for a long time, and we are happy to finally have Professor Borah with us. Thank you, sir, for accepting our invitation. We are very happy to have Professor Baba Kumar Sarma from IIT Guwahati and MTTS Stress. We request Baba sir to say a few words. Over to you, sir.
Thank you, Kaveri. Good afternoon. So on behalf of the MTTS Trust, I welcome you all to this lecture series on Riemann mapping theorem via the Dirichlet problem, organized by Curry Leaf jointly with the MTTS Trust. Yeah, most of the audience present here, at least in Zoom meeting, may not need any introduction to the MTTS program. However, for the benefit of others, also those who are viewing on YouTube, let me say a very few words about MTTS. Undoubtedly, Mathematics Training and Talent Search, that is MTTS program, is one of the most popular and significant training programs in India. MTTS has been running since 1993 and has made an impressive impact on the mathematical scenario in the country. Please note that this MTTS programs, this is not a program organized by an institution. Okay. Rather, this program is being run for last 3 decades by a team of people involved in mathematics education. So that itself says a lot, that uninterrupted program for last 3 decades running. Okay. And it's actually expanding both in quantity and quality. It is enhancing its quality as well. So that itself says a lot about the program. The aim of this program is not to give routine lectures. Rather, the program is to stimulate the participants to think and discover mathematics and mathematical results on their own. And the program has inspired also some other discipline, people in some other discipline, including physics and statistics, to organize programs in similar methodology. These MTTS programs, they evolved through years, over the years. Initially, it was started at 2 levels. There was single summer training program, 4-week programs every year. At 2 levels, one is for level 1 for degree 3rd year students, and the second level for MSc 1st year students. After a few years, actually it was felt that the students at lower level itself, I mean at the beginning when they start actual serious mathematics, they should be started giving being given training. So another level, it is called level O. we don't call it level 0 because no one is 0. So level O program to this, this was added in after 6 or 7 years of the starting of an MTTS program. Apart from these MTTS summer camps, there are also other programs called Initiation into Mathematics. As well, it was mini MTTS programs. This is usually 1 or 2 weeks programs, 2-week programs, and they are organized across the country in nook and corners, starting from, say, Mizoram to Kerala to Jammu and Kashmir to Rajasthan. So it has reached through these mini MTTS programs. Actually, MTTS has reached nook and corners of the country. Then last, when this pandemic started 2 years back into March 2020, so there was a challenge. So everything was stalled. In fact, our summer program, MTTS program that was to be held in May, June of 2020, that had to be abandoned. But that was a challenge. However, this the challenges of this pandemic also gave rise to certain avenues, like say online programs. So for 2 years, these MTTS summer camps were held online, 2020 and 2021. And apart from that, there are some other programs which have been introduced and being run by the MTTS Trust. One is WebCM, Online Foundation Course in Mathematics, and some other are say short courses and open forum lectures. So these are even some of the mini MTTS program, or that means Initiation into Mathematics programs are, had been organized online. So this has also has, though, blessing in disguise. So this the new mode of this having programs, online programs, that has actually given us some more opportunity to reach more students. Now, I'd like to say a few things why these MTTS programs have been so successful, why it has made so much of impact. And the other thing is that why it has been running for last 3 decades uninterrupted. So, it is not a very easy thing. It's not a usual thing that is a kind of program. It is run by a group of people for 3 decades. So the very first thing is that the center of this entire exercise is Professor S. Kumaresan, whose untiring visionary leadership has kept us moving. And in fact, Professor Kumaresan has been leading from the front at every point of time, even during the time of distress because of this pandemic. In fact, it was Professor Kumaresan who made it possible that we can organize the MTTS programs on online platforms. The second thing is the success of MTTS. It is due to the unique methodology. Okay. As I said, that it is not to give a lot of mathematics to the students, rather to teach them how to learn mathematics. So, and that unique methodology is the prime thing in MTTS programs. And the second point is that this methodology is student-centric. So it adopts, or it basically takes care of the students rather than giving from the above. It is from the bottom. At the bottom, it is the training it runs depending on the quality of the students, and that's why these are as a result. In fact, one to all, every student who participates in any of the MTTS programs benefits. And the third one is that why this is so successful is that the MTTS program is ready to change and adapt to the new challenges. So new methodologies, new kind of techniques. So this is always done. And one can see that in every program, MTTS program, something new is introduced. So far as funding of these MTTS programs are concerned, is that the main fund for MTTS programs, it comes from NBHM, National Board for Higher Mathematics, DAE, Government of India. However, of late, the government funding is shrinking. So at one hand, the funding is shrinking. On the other hand, we have enhanced capabilities, more alumni expressing to participating in MTTS activities. The academic manpower for MTTS has increased, in fact, manifold over time. And recently, in fact, this increase is actually in a much rapid scale due to the MTTS online programs. And as a result, the MTTS family now has, it has more capability. It can reach to many more needy students, whereas the funding is limited. So, the trust has started receiving donations recently, last 2 years. So donations, and the donations are entitled to exemption of income tax under 80G. So we need to reach to the prospective donors so that we can keep on having more programs, reach to more students. So probably MTTS alumni can also help us in reaching donors. And these details of this donation to MTTS Trust is available in the MTTS website. And at times, probably, at times even crowdfunding, it can also help a lot. So that's so far as the finance is concerned. So let me say a few things about Carathéodory. So for the MTTS Trust or the MTTS family, the core family, the reaching to the alumni had always been a matter of concern. And there was a provision of registration by the alumni through MTTS website. However, until recently, there was not much success on that front. But now we can see that the alumni of MTTS is much more visible through this Carathéodory platform. So when some of the alumni expressed their wish to start this platform, Carathéodory, Professor Kumaresan was really very happy, and he helped all the way for creation of this Carathéodory. And MTTS Trust is very happy that it has come up. So we are extremely happy to see Carathéodory shaping up and its activities since its inception. The participants of MTTS program in the last 30 years, it's a big number. It constitutes a large alumni, and there is a tremendous scope of changing the mathematical scenario in the country, even if a fraction of the alumni makes a collective effort through this platform, Carathéodory. So there can also be hand-holding by the seniors in the alumni of MTTS to the juniors. So I wish all my best wishes for the fruitful journey of the Carathéodory. And finally, let me wish my best to the speaker, Dr. Diganta Borah. I fondly remember him as a participant of MTTS program held at IIT Guwahati about 20 years back. So probably he was in the second or third year of the MTTS organized in IIT Guwahati. And second thing is that I'm also happy that he happened to be a student of our MSc program at IIT Guwahati. So we have a lot of connections with Diganta Borah, so far as a member of IIT Guwahati is concerned. I'm sure that this series of lectures on Riemann mapping theorem delivered by Dr. Borah will be fruitful to the audience and a memorable experience for all of us. Once again, I welcome all of you for this series of lectures on behalf of the MTTS Trust. Thank you all.
Thank you, sir. Thank you, sir, for your kind words. Now we request the participants to keep their audio muted. If you have any question, you may type in the chat box in the Zoom. Also, you can type in the chat box of YouTube. Now, without further delay, we request Professor Borah to start his lecture. Over to you, sir. Thank you.
Thank you, Kaveri, and thank you, Baba sir, for the nice introduction. So let me, begin by thanking the Carathéodory organizers for giving me this opportunity to speak here. So I hope I am audible and visible, right?
Yes.
Okay. If there is any question in between, probably some of you will. It will be on the chat box, right?
Yeah, we can relay to you if you.
Yeah, because I I may not frequently check the chat box,
Sure.
so let's do that. Yeah. Okay. Let me share the screen.
Okay, it is better that those who have question, you can raise hand. Then we will divert to sir. Okay.
Sure. Yeah. Okay. Shall I start?
Yes, please.
Oh. Okay. So the goal of this series of lectures will be to learn a proof of the Riemann mapping theorem based on the original ideas of Riemann. Riemann stated his theorem in 1851 in his PhD thesis. So let me first write down the statement of the theorem. So here is the statement in its most general form. So suppose you have a domain. So let D be a domain. D be a simply connected domain. So simply connected means there is no hole. Right? So if you take any closed loop in D, you can actually continuously shrink it to a point. So if you have a simply connected domain in the complex plane, and also D is not all of C, then D is biholomorphic to the unit disk, which I'll write as D. This is the disk centered at 0, radius 1. So here, so when I say D is biholomorphic to the unit disk, I mean that there is a biholomorphism from D to the unit disk. So biholomorphism means it's a holomorphic map, which is invertible, and inverse is also holomorphic. So biholomorphism means holomorphic plus it should be invertible plus inverse should be holomorphic. Actually, it's a fact that if you have a holomorphic map which is invertible, its inverse is always holomorphic. So this part is redundant, but we don't need to go into that. So let me add this without without going to that inverse function theorem in complex analysis. Okay, so this inverse is holomorphic. This is a fact. You don't have to actually assume this. This is always going to be true. And we say that say omega is biholomorphic to morphic to omega prime if there is a biholomorphism. From omega onto omega. Okay, so biholomorphism is it's nothing but a conformal map, right? So this is also a conformal. So any simply connected domain, which is not all of C, is biholomorphic to or conformally equivalent to the unit disk. You should know that each of this condition is hypothesis. Actually, there are two hypotheses. One is simply connected, and one other is not all of C. Each of them is actually a necessary condition, because if D is biholomorphic to the unit disk, because a biholomorphism also is a homeomorphism, right? Because holomorphic maps are continuous. So, and the inverse is also, you are assuming holomorphic, this is continuous, right? It's a homeomorphism. So if D is biholomorphic to the unit disk, so D is also homeomorphic to the unit disk. And since the unit disk is simply connected, so D has to be simply connected, right? Simply connectedness is a topological properties. It means invariant order homeomorphism. So this is a necessary condition. The other condition that D is not all of C is also necessary, because you see, if there is a holomorphic map from all of C to the unit disk by Liouville's theorem, it has to be constant. Right? Bounded entire functions are constant. It cannot be inverted. So both the conditions are necessary, and the theorem says that, well, they are good enough, like they are sufficient. If you have these two conditions, the domain has to be biholomorphic to the unit disk. This is very remarkable, because you see, in general, simply connected domain could be very, very weird. Right? So can be like very complicated. We can't even imagine. Okay. But you don't have to assume that. We are not assuming this bounded. So and this theorem says that because there is now a biholomorphism from this to the unit disk, let's call it say so if you have certain result on the unit disk, it's most likely you would be able to actually bring it back to this complicated region, right? It's a truly remarkable fact. So now the proof that usually taught in first course in complex analysis is due to Carathéodory. Okay, so this proof is based on the so-called Montel's theorem, which says that if you have a family of holomorphic functions, which is locally uniformly bounded, then the family is compact. That means you pick up any sequence from this family, there will be a subsequence which will converge locally uniformly. That is the Montel's theorem. Anyway, I'll actually quickly recall this proof also, the standard proof also. Though our aim is to understand the proof, using Riemann's ideas. So the Riemann's proof, his proof actually had certain difficulties. His proof is based on the so-called Dirichlet problem.
Just one question. So domain is open set, right? Just open set.
Domain is open and connected.
Okay.
So let me. Domain means domain open and connected.
And unit disk is also like the open unit disk.
It is open unit disk. Yes. So,
Okay.
right. So D is this Z in C is that mod set less than. So this is the open unit.
Thanks. Yeah. Sure.
Right. So let's see, there were certain difficulties in Riemann's proof. His proof is based on the Dirichlet principle or Dirichlet problem. Which basically he only named this Dirichlet problem. Okay, so it was his. It was coined by him. So the problem was that at that time, it was not well established. Basically, a method for solving the Dirichlet problem. It was not well established. Okay, so actually, let's try to let me sketch Riemann's method to understand where exactly the difficulty was. Okay, so today's lecture will be mostly kind of some motivation, some history, and the actual work will actually mostly begin tomorrow. Okay, so let me point out. So sketch of Riemann's method. So once we understand the difficulty, we'll actually, in the upcoming lectures, we'll develop a method to overcome that difficulty. So, so here is how he, try to attack the problem. So suppose so first of all, he assumed that, so let's assume D to be bounded. Assume D bounded, okay. Later on, I'll show you that without loss of generality, we can always do that. In the proof of the Riemann mapping theorem, it's always possible to assume that D is bounded. We'll see this later, today itself. And suppose there is suppose F from D to D is a biholomorphism. Is a biholomorphism. Okay. The idea is that try to see if F satisfies certain equation, and then one would expect that solving such an equation you can construct a function. This is a biholomorphism. Okay, so it's like walking kind of backward. Now, if such a biholomorphism is there, so there will be some point in D which will go to 0, right? And suppose F of some point Z0 is 0. All right. Now, F is a holomorphic map with a 0 at Z0. We know how it has to look like, right? It is F is going to look like Fz is of the form some Z minus Z0 power K into some holomorphic function ZZ on D, Z holomorphic, and Z does not vanish. Right? This will learn in previous analysis course. But here actually you can say something more. Remember, F is a biholomorphism, so in particular it's injective. And so you can immediately say what is K. So this K has to be, so since K is since F is injective, So this k has to be, so first of all, this k has to be 1. It cannot be more, right? And the second, because f already vanishes at z0, it cannot vanish anywhere else. So that means this function z, cannot vanish anywhere away from z0. It also does not vanish at z0. So that means z is nowhere vanishing. Only. Right? So f is of the, so I can, now it's, you see, you are working on a simply connected domain and you have a nowhere vanishing function, non-vanishing function. We can talk about a, branch of logarithm of z, right? So I can write, so therefore z is of the form e power some hz, where h holomorphic on d. It is the standard fact from complex analysis, because d is simply connected. Okay, so here I am using this, d is simply connected. So we have, so that means we have, so that's f, therefore, so this biholomorphism has to look like fz is equal to z minus z0 into e to the power h of z. So now our aim is to find this hz such that f becomes a biholomorphism, right? So if you try to, so because any biholomorphism has to look like this, so aim is to find suitable h. Now you see again, you are working on a simply connected domain, and we know that on a simply connected domain, harmonic functions have conjugates, right? So if I write s is equal to u plus iv, u is the real part, v is the imaginary part. So if it is enough to find this guy, enough to find h, enough to find this real part of h, right? Then we can find conjugates, and with some work, maybe some conjugate will work. So this was a crucial point in Riemann's method, to work with the real part of the function h. Right? So f. So now let's try to see. So f has to look like. Sorry. So fz is now z minus z0 into e power uz into e power I vz. And we hope that if we can find a suitable u, then v also we can determine, and then with some work, maybe that f will work. So since we are only interested to find u, so let's try to get rid of v. So what you do, so you simply take modulus of this, right? So mod of fz is equal to mod of z minus z0 e to the power uz. So u is real, right? Real part. So e to the power u is real, positive, non-negative number, and then e to the power. So this gets it. Anyway. All right, we are more or less here. Now you see, so let's use the fact that f is a biholomorphism now again. So if z goes to the boundary of d, because f fills out all of the unit disk, right? So mod of f has to now go to 1. Then mod of f z goes to 1. This means that in this equation here, if you look at, so this quantity now goes to 1, this product. So that means the exponential of u power. So this would mean that, let's write it down. So this would imply that e to the power uz, this will go to 1 upon z minus z naught, which would mean that uz will go to log of this 1 upon mod of z minus z naught. That means minus log of z minus z. So this is important. So, so remember, you want to find an q, and here is a condition that you want to consider. So u is a harmonic function, and you should go to as z goes to the boundary of D, it should you should go to minus log of z minus z. So now our aim is to basically find a harmonic function on the domain D, on the simply connected domain D, such that its boundary values are given by minus log of z minus z naught. It's a Dirichlet problem. You want to find a harmonic function with specified boundary values. So, so Riemann proposed that it can be done in the following way. So, at this test, so let me write down what is our aim. So aim is to, now the new aim is to find a harmonic function.
Yeah, some student are raising their hands.
Okay, please, Sushant, yes.
Yeah, you can unmute now.
Okay,
Sir,
very good. Oh, sorry, sir. Please continue.
Yeah, please go ahead, Sushant.
Very good evening, sir.
Yeah.
Sir, I had a doubt in the statement actually. Sir, can you please go back to the first screen? Thank you. Yeah. So we are saying that then D is biholomorphic to the unit disk, right?
Yeah.
So,
Yeah.
so we can see complex plane as R2, right? So we can see that simply connected set can be molded to the disk if they are homeomorphic.
Right.
So what extra is this biholomorphism is giving us to?
This is conformal. It's angle preserving. Okay,
So
that
can
is something.
yeah.
So in complex analysis, you might have seen that if you have a function which is derivative is non-zero, right? Complex derivative is non-zero, it preserves angle.
Yes, sir.
So was that your, so what exactly, so you mean, so can you repeat your question? Am I?
Yes, sir. So like in this statement, I can see that yes, homeomorphism is giving us that we can mold this simply connected set to the disk.
Yeah.
But what extra is this biholomorphism is ensuring? That,
Oh, yeah,
is
that's what. So it's a stronger condition than homeomorphic, right? So it's holomorphic itself is something more than you can, the complex derivative exists. There's something a stronger condition. So it's much more than saying it's just homeomorphic.
Yes, sir.
Okay. This, for example, as I say, it will preserve angles. Okay.
Yes, sir.
Right. Yeah.
Okay, thank you, sir.
Yes.
Yeah, there is one more raise hand. Nitin?
Yes, sir. Sir, can you please tell me on second page how mod S goes to 1 as Z goes to on the boundary point at the boundary of D?
Right. You see, F maps the domain D to the unit disk.
Yes, sir.
Right, and it's a homeomorphism, right? So the boundary So if you approach the boundary from on the domain side, you have to spread out to the boundary on the codomain, target side, right? So
Yes, sir.
that's why if z goes to the boundary, fz will mod of fz will converse to 1. I'm not saying fz will converse. Okay, that is something a big question. The limit of fz may not exist, but what you can definitely say, mod of fz will definitely go to 1.
Okay. Thank you, sir.
Yeah. Okay. All right. So let's go to the previous thing. Right. So we have now learned that this problem, to tackle this problem, basically our aim is now to find a harmonic function u on D with boundary values minus log of z minus z0. This is a Dirichlet problem. So Riemann also proposed how to find a solution to this. Let's see. Right. So for this, actually Riemann. So first, let's review. So Riemann proposed. Riemann proposed. So first of all, assume. So actually, in the statement that Riemann's statement of the theorem, he also assumed D to be the boundary of this to be piecewise smooth. Okay, so you will see why. So assume, but the most general form, as I say, does not require this piecewise smoothness. Any simply connected domain is fine. So assume D is piecewise smooth. Then you say that you can find, so say, harmonic function with boundary values by minimizing the following integral. So minimize. So let's look at the following integral on D. Try to minimize it. So this square, say, let's write d3 dx square plus d3 square dx dy. This is called a Dirichlet integral, and this integral. So this is called the Dirichlet energy of phi. So let's denote it by p phi. So it's a functional actually. So you are taking a function to a real number given by this integral. It is. So Riemann said that you minimize this guy because one can show that once you assume the boundary to be piecewise smooth. So if a minimum exists, if a minimum exists, say u, then by appealing to Green's theorem, one can actually show that the Laplacian of u has to be 0. So I should also say that we want certain boundary condition. So minimize this subject to. So let's write down. Minimize this guy subject to. So there is not enough space. Maybe I write here subject to. The boundary is phi is equal to f on delta d, not f. Maybe. So our boundary vectors are minus log of z minus z naught. So some boundary vectors phi is equal to some say phi is equal to c, some c on delta d. So this is a general. So what Riemann called the Dirichlet principle. So you have some boundary function c continuous, okay, and then you try to minimize this Dirichlet integral. And if a minimum exists, then because the boundaries you are assuming piecewise smooth, you have the so-called Green's theorem from calculus. One can actually show that Laplacian of u has to be 0. Okay, so that means U will serve as a solution to the Dirichlet problem, right? It will be harmonic and it will have boundary value C. Right? We can take C to be this minus log of Z minus Z naught. Now the problem, so this is so far so good. The problem is that it was so Riemann actually took it for granted that there is always a minimum. So Riemann took it for granted that a minimum always exists. Okay, so if the domain is piecewise smooth, simply connected, bounded, okay, with all these conditions, so Riemann say that minimum always exists. However, at that time it was not known. It was not clear if there will always be a minimum. That was the difficulty. So Riemann's proof was considered to be incomplete at his time. Okay. So it was Osgood who finally, showed that. So this is around 1900. So Osgood. So he showed that on any simply connected domain, not necessarily, so without any assumption. So no piecewise smooth bound, nothing boundedness, no other condition. So on any simply connected domain, one can actually solve the Dirichlet problem. So the Dirichlet problem is solvable on any simply connected domain. Let's it's good to, so any bounded simply connected domain. Sorry, I should mention bounded simply connected domain. So this is needed, bounded simply connected domain. But for the proof of the Riemann mapping theorem, as I say it, and I will also point out that boundedness is not necessary. We'll see. So this Osgood's. Yeah. Any questions? Shami.
Yeah. So when the minimum exists, like suppose it exists, so then the U may not be. Will it be unique? Can we say something?
So no. See, of course. So this all what I am saying is only kind of it's a sketch of Riemann's proof. Okay, so it's not a proof. We are going to discuss the proof in detail in the upcoming lectures. So there are some more difficulties actually. Once you find this U, of course, you have to find some V, and then you have to look at this H that I was talking about. Then F, and then showing that F is also kind of 1, 1 on 2. That is also kind of not obvious. Okay. So these were kind of, but they were kind of less kind of difficulty, because this was the most severe difficulty, because it was not known whether this Dirichlet problem could be solved on this bounded simply connected domain. Other difficulties still could be resolved. Okay. Anyway, we'll see in detail in the upcoming lectures.
So just in the statement of the theorem, that biholomorphism, is it unique? Can we say something?
Yeah. You have to put some more condition. Otherwise, see, for example, you can rotate after going to the disk. You can rotate, right? So it may not be unique. So I'll point out what are the conditions needed to say that the biholomorphism is unique.
Okay.
There are conditions. Yeah.
Sure.
Right.
Thanks.
Okay, so Osgood's once Osgood's showed this, that the Dirichlet problem is solvable on any bounded simply connected domain. So then that was actually considered to be, can be considered. This was the first actually complete complete reasonable proof of the Dirichlet problem. The Riemann mapping theorem. And so we are basically our goal will be to understand this particular proof. Okay. Now coming back to but as I said, I want to discuss the other proof also. The standard, usually the proof that is discussed in the first course, the Carathéodory theorem. So somehow, this Carathéodory proof, it's kind of it doesn't use any potential theory, any Dirichlet problem. It depends only on function theory. Okay, so it somehow established itself as the most standard proof. So let me, So let me today, quickly go through how the Carathéodory proof given. So, and then we'll try to develop a method for solving the Dirichlet problem, and then we'll try to prove the Riemann mapping theorem along the lines envisioned by Riemann. Okay, so today let me only start with Carathéodory proof. So actually, it was Carathéodory, and Carathéodory proof was simplified by Kobe. So we'll basically discuss this simplified version only. So there are essentially two steps in this proof of the Riemann mapping theorem. So to explain, let me start with the following. So here I have a simply connected domain. So and I want to show that there is a biholomorphism from D to the unit disk. So just give me a second. So Soumya or so can I speak to any of the organizer? Soumya?
Yeah. Hi.
So am I supposed to give a break or I can continue?
Yeah, I think that's a good idea. So you can have it now.
Yeah, sure. Maybe not more than 5 minutes, maybe. That's okay, right?
Yeah.
Okay. So yeah, so we'll take a very short break, at most 5 minutes. But I am here. Okay, if you have some questions, you can discuss.
Exactly. If you have any questions, you can ask. This is a good time.
Right.
So yeah. So we again start at maybe 3:56.
Sure. Nitin, you have a question?
Sir, can you please explain that part e phi x function, sir?
Yeah, sure.
No, sir, on the third page, sir. Third page.
Oh, this is 1, 2, 3.
Yes, sir. E5x.
Oh, okay. Yeah. So see, this is a Dirichlet integral. So you take a function phi on D.
Yes, sir.
Okay, and then you look at this integral d phi d. So because you were trying to find some harmonic function. So assume it's sufficiently differentiable and all these things. And
Yes,
you look
sir.
at this integral, d phi dx plus. So this is just basically mod of gradient of phi square, right?
Okay, sir.
And yeah, so you look at this double integral, call it Phi. So capital E, you are basically thinking of as a functional. So it is taking a function to this real number given by this integral.
So then how?
So this is So how this is something like it's a calculus of variation problem. So one can still talk about how to minimize all this data. Okay, so you want to find a minimum for E. You want to find a function u such that E of u is less equal to all the E's. Okay, one can talk about that, and then if such a u exists, and then one can show that the Laplacian of u has to vanish. Okay, you can proceed like the intuition is similar to what you learn in calculus. If you have a critical point, the derivative is 0, and so on. So you can try similar sort of things. Okay, so yeah, but we'll do it. We'll not try it this way. We'll do it in some other way. Okay, which is kind of easily understandable. Yeah.
Okay. Thank you, sir.
Okay. All right. So maybe we can resume now.
Yeah, please.
So Carathéodory's proof. So this appeared in 1912. This is based only on function theory, not on potential theory. And this is kind of this turned out to be the most standard proof now. So let's quickly recall this proof. So as I said, there are 2 steps. So let's consider the following family. So F to be set of all functions F from D to the unit disk. So you fix a point. So let Z0 is in D, and you consider this family. So such that F is holomorphic. Injective, and F of Z0 to be 0. We consider all holomorphic injective functions from the given simply connected domain D to the unit disk, which takes the point Z0 to 0. See, our aim is to show that there is a member in this family which is also surjective, right? But before that, we first of all need to know that this family is non-empty, right? Because I have assumed no assumption actually. D is any simply connected domain. So we need to show that there is at least some injective holomorphic map to the unit disk, right? So that this family is non-empty. That is the first step. So step 1. So here we want to see that F is non-empty. So let us see why. So what is given to us? So we know that what is given to us is that D is simply connected, and so what is given to us? D is simply connected, and D is not all of C. So that means there is at least one point in the complement of D in C. But for a moment, let us assume that suppose the complement is quite big. So D is say something like this. And we are assuming that there is at least some disk, say centered at A, radius r. Okay, this is only an assumption. We'll see that this is not necessary. Only for, in this case, it would be easy to see that there is this family is not. Assume some disk centered at R. This is inside complement of B in C. In this case, you see, it is easy to come up with a member in this family, because, for example, if you look at the inversion along this circle, if you look at the inversion along this circle, it will bring everything outside to inside, right? And in particular, it will bring this D also. D is inside, outside this. This is the complement, right? So this will also, go inside this. So if inversion along this. But then, by means of a translation and dilation, I can go to the unit disk. Yes, so once you are inside this, you can make suitable translation, and dilation. You can go to the unit disk, and you can also, make sure that this point Z not goes to 0. That's not a difficult thing. So if the complement is quite big, then it is not a problem to come up with a member in this family. So I am anyway going to write down a member in the general case also. But the problem is the complement may not be in general big. For example, if you think of, say, the slit plane, if you look at the slit plane, so maybe so the slit plane is this real of Z positive is deleted, right? So here the complement is this positive real axis. So you see that there is no disk, right, inside the complement. But nevertheless, what happens is that you can actually widen this complement. Okay, so what you can do, so even let's take it more complicated. Say let's take something more complicated, simply connected domain, something, maybe something like this. Say. It's just it can be I don't know, it's something. So everything else, say for example, again it is only a picture. So apart from this blue line, everything else is there. So this is your domain. Everything else apart from this could be, go on forever, this line. So this is your D. So in this case, in the complement, you can't draw a disk, right? But what I'm saying is that it is still possible to widen the complement by means of a conformal map, by means of a Bialov physics, and then you can put a disk inside. So the first step is, so let's try to see how to widen this. So let's take a point, say something A here. So my aim is to map D to something whose complement contains some disk. So here is what you can do. So you look at the following function, Z minus A. Because A is in the complement, Z minus A is non-vanishing, right? Non-vanishing on D. Because A is in the complement of D. So I can, take branch of square root, right, of Z minus A, because it's a simply connected domain. A function is non-vanishing. I can talk about square root. So there exists C holomorphic, Z holomorphic on D, such that, so Z is the square root of Z minus A. So ZZ square is equal to Z minus C. Okay. This you can always do. Simply connected domain, non-vanishing function. You can talk about because you have a like, branch of logarithm and so square root. Okay, I will show that this map will take D to a domain whose complement is big. So Z. So I want to show that Z is something like this. So Z will map this guy to something like something like this. So D will be something like this. Let's show this. So first of all, you see Z is this guy is injective, right? Because if you have ZZ is equal to ZW, then squaring it, I get Z minus A is equal to Z minus, W minus A. This is squaring. And this immediately gives Z is equal to W. Z is an injective map. So Z of D is a holomorphic function. It is non-constant injective. And so Z of D, this is an open set. So this is, so let's call this, so Z is open. This is an open set, right? So Z maps this D to ZD. So this is going to be ZD will be something like so say maybe we don't know. So ZD. Okay, sorry. This picture is kind of misleading. So ZD is open. I still need to see something before drawing this. So I want to understand the complement of this guy. So here is another observation. So the domain ZD and the domain minus Z of D, this is actually empty. So Z, D, and Z minus ZD do not intersect. This is again easy to see. You see, any point here look like something like ZZ, right? And a point here is going to look like some minus of Z of W. But if they're equal, again, if you square it, you get the left hand side is Z minus A, and the right hand side is so minus of ZW square. But that is ZW square and W minus A, that would imply Z is equal to W. But then this cannot hold, right? So this, if you continue this implies, so ZZ is actually, because ZZ is minus ZW, ZZ is minus Z, which implies ZZ is 0. That is not possible, right? Z is non-vanishing. On D. So yeah, because ZZ is equal to 0 implies Z is equal to A, and A is outside D. So this is a contradiction. So these two sets ZD and Z minus ZD do not intersect, but they are kind of intuitively they are of same size, right? ZD minus ZD is negative of the numbers in ZD. So that's why the picture would be something like, say, this one. This is your so this is minus Z of D. Here is your G of D. Right. So ZD is more or less, as much big as kind of minus ZD is as much as big as ZD. So you can definitely find a disk here. So there is some disk here. Right. This is because ZD is an open set. Minus ZD is also an open set. You have some disk here. So say this is let's not take A. A we have already used. Maybe some B. Maybe some B. And various are. Okay, so there is some, so there exists. So there is there is some disk centered at B, radius R, inside minus C of D. So that means this is in complement of D, right? So this is C minus D. So you are done, right? As we saw earlier, you can actually now you can find a map from GD to this disk. You can write down the map. So let me write down for sake of completeness. See, any point if you take here, it is of the form ZZ, and because it is outside this disk of center B radius R, so mod of ZZ minus B has to be bigger than R, right? Because it is outside the disk. So this would mean that R divided by mod of ZZ minus B is strictly less than 1. So you should take F to be, so take F Z to be simply this function, R divided by mod of, not mod of, ZZ minus B. So this maps the domain D into the unit disk. Okay. Of course, the point, Z naught. So this you can, as Z is injective, this is also injective. Only thing that may go wrong is that the point Z naught that you want it to go to 0, that may not happen, right? But that's not a big deal. You can simply consider an automorphism of the disk, the conformal map of the disk onto itself. We take this point Z naught, so this point F Z naught to 0. So compose. So here, compose. Maybe I go to the next page. So here is the map I am considering. Fz is divided by Zz minus B, right? So this is from what I'm sure is that this is D, taking D to D. So if you want Z naught to go to 0, so all you compose with a map like, so these are automorphisms of, so the typical automorphism of the unit disk look like, say, T, some point P, Tp of Z is Z minus P by 1 minus P bar into Z. Okay, so this is D to D automorphism. So this is biholomorphism. Right, so this maps are biholomorphisms. So you can simply compose, so T of something here with F. The something is nothing but R divided by Z at Z naught minus P. Okay, so is a map from then D to D, and it will also take Z naught to 0. So this proves that the family is non-empty. Okay, so showing that this family is non-empty is not difficult. And this step also shows you that, you see, you can always assume in the proof of the Riemann mapping theorem, D to be bounded, thanks to this theorem, because you have already produced a map, F, which takes D injectively into the unit disk, into this bounded domain. Okay, so you can always assume that D is bounded without loss of generality. Okay, so this will be using later also. Okay, so that's fine. Now, once I know that this family is non-empty, so let me, quickly tell you how to proceed in the second step. I will leave the details for you because you have seen this, and I will only give the motivation how to go in the second step. So here I want to show that there is a member in this family which is also surjective, right? Now, so let's draw a picture. So here is, you have some domain D, could be very complicated. And so here is the unit disk. Actually, let's use some different color. So this is your D. And now I know that I can map it into the unit disk. So F, say F is a map, which is mapping it to a unit this. So F is, so this is going to look like something. So F, say F is, this is the map F taking into the unit disk. Now, so if you want this F to be surjective, then what you want is that this blue part should fill out all of the, right? You should actually, for F to be surjective, then you should fill out all of the unit disk. Okay. So if F is surjective, then it should fill the F of D should actually fill out the like whole of D. So that means starting at, so this point Z0 is going to 0, right? So this is say Z0, and this is F is taking this to this 0. So starting at 0, you should spread out. You should spread out as far as possible, and eventually you should reach the boundary of D, so that F becomes surjective, right? So intuitively, you see, if you want to start at 0 and spread out, so spread out, very as far as possible. So intuitively, you should take F to have very high velocity at Z0, right? If the velocity at Z0 is very high, then it will quick out very, spread out very quickly, correct? And so the chances of it hitting the boundary of D is small. This suggests that once you try to, again, this is intuitive, but this intuition tells us that. So we consider, the derivatives of this maps at Z0 and try to maximize this. So try to, maximize this quantity where F is in F. So let's call this alpha. So our intuition says that if we can maximize this quantity, so that would mean that I have a function with kind of highest velocity at Z0, and I believe that this will spread out very quickly to reach the boundary of D. And so this will, give us a surjective map. So it is intuition. I consider this, and you should note that this is definitely positive because I have already produced injective maps into the disk, right? Injective holomorphic maps. So derivative cannot vanish. So this will have to be, so at least there is some F with F prime Z not non-vanishing. So this supremum will be non-vanishing. Okay, so this is a positive number. Okay, so now I want to maximize this. So here comes the Montel's theorem. It says that. So let's first write down something. So this is a supremum. So I can find a sequence converging to this supremum, right? So let Fn. So this is a sequence in F. So we says that Fn prime at Z0 converges to alpha. Sn equals to. Okay. So this is because property of supremum. You can do that. Now note that this family Fn is uniformly bounded. Right? It's uniformly bounded by 1. All the maps are to the unit disk. So Montel's theorem says that so by so let me write in the next page. So Montel's theorem says that there is a subsequence which will converge locally uniformly. Okay? So by Montel's theorem, so I'll not go into the the details of these theorems because our ultimate goal is something different. Today I'm only recalling what most of you probably have seen in first course. So by Montel's theorem, So there is a subsequence. So let me rename this subsequence as Fn itself. So by Monte's theorem, so passing to a subsequence. Fn converges locally uniformly to a holomorphic function f from D2. Now you see, although the functions fn were D2, the unit this, but you are taking limit, right? Limit of f and z. So it may happen that limit goes to 1. Okay, so even if so all z like fn of z are less than 1, fn limit could be actually 1. So there is a priori I do not know, so it may go to the unit this closer. But I'll show that it is not the case. You have to be actually inside this. And that is because look at f prime. So I have a function f, now f prime at z now. What can I say about this? Remember, this f is the limit of this thing, right? Fn. But if a sequence of holomorphic function converges locally uniformly, the derivative also converges, right? By Wester's theorem and all, you can show this. So this is also true, right? Let's put a mod here. This is alpha positive. So derivative of f does not vanish at z0. So in particular, so then therefore f is non-constant. And here comes the so-called Hurwitz theorem. So you have a sequence of injective holomorphic maps. They converge locally uniformly to some function f. The Hurwitz theorem says that the limit is either constant or has to be injective. So it is non-constant, so f is injective. And hence by the open mapping theorem, so f of the f cannot go to the boundary. So it has to be fd has to be open. So it has to be actually inside D. Right? And I also know that f being the limit of fn, which are family members of the family. So f of z0 is 0 because this is limit of fn at z0. So therefore, this is actually coming from the family. In other words, I have a maximizer for the derivatives at z0. So this function f, this is a element in the family, and it also maximizes the derivative. So the final step here is to show that this function is surjective. So the claim f is surjective. Okay, intuitively we know, right? In fact, we try to maximize the derivative, so we know that this will kind of spread out very fast. But suppose it is not. Suppose not. Suppose not. So what would it mean? So I'll only draw some pictures to show how to find a contradiction in this case. So here is a picture. So you have this, say, domain D. And you are already in the unit disk now. Okay, so by means of this map F. And you are assuming that the image is not all of the unit disk. So the image is something like, say, it definitely contains 0 because Z0 goes to 0. So image is, say, something like this. But you are assuming that it is not surjective, means that there will be something outside it, but inside the disk. Right? So there is some point, say maybe So take some A. Let's choose another color. Okay, so this is how so if you assume F is not surgical, this is how the pixel is more or less going to look like. So there is some A outside the image of F. So the idea is to expand this this region, this blue colored region, remaining inside it. So I want to expand this. Okay, so I will show that this can be expanded, and thus I can produce some another function in the family with more derivative than F at Z0. Okay, so let's try to expand this blue image of F. So how would I expand? How to do that? How to expand the set inside the unit disk? See, if you so again, this is very intuitive. So if you have a real number between 0 and 1, okay, real number x less than 1. How do you make it bigger? You simply take square root, right? If x is less than 1, if you take square, it becomes smaller than x. If you take square root, it becomes bigger. Right? So the idea is to here also we want to do the same thing. We want to take square root of the numbers here so that we get a bigger set. But there is a certain difficulty here because the 0 is here. So you have to, we want a branch of square root, right? So you have to make sure that 0 is not there. But that's not difficult. So what you can do here, you simply compose F with some automorphism of the disk so that 0 is not there. Okay, so let's look at this thing. And you look at, so this A is outside. So you look at this thing, PA. Remember, this was the map. Z minus A, 1 minus A was standard automorphisms of the disk. So what does this TA do? So it will take A to 0, but then it cannot take anything else to 0, right? So that means TO of F, so if you look at this composition, TO of F, that cannot vanish, right? It has to, because TO of F never takes the value A, and TA vanish only at A, so the composition will not vanish. So now if you look at the image of this blue colored region, it will be, it will avoid 0. Maybe something like this. And 0 is, so 0 will be here now. So I'll make it red color because A is coming to 0, nothing else is coming to 0, and F does not take the value A. So this is now, the image will be something like this. So now you take the square root, the square root of this region. You definitely don't go out of, so let me draw one more disk. I still have some space. So here I am taking, this is branch of square root. Okay, so this I believe it will expand this. Image 0 will still be avoided here. Okay. So this once you compose with this square root function, so then the image will be enlarged, and then we know our intuition says that the composition now, this S, T, A, and F, this composed map should have more derivative than F at Z0. But there is one slight modification you need, because this composition ultimately you see Z0 is this Z0 is not going to 0 under this composition, right? So so you have to make sure that Z0 goes to 0 so that you get a map in the family. So you can that again you can do by simply again looking at another conformal map. So of the unit disk. So let's track where Z0 is going. Z0 under F is going to 0. 0 under TA. So let's use some color like maybe this yellow color will do. So this is Z0. So under F it is going to 0. So when you apply TA, you are basically going to so 0 is going to minus a, right? So minus a will be somewhere, say here. And then here you have square root of minus a. Rather, I will write s of minus a. This is square root of function. So this need not be 0. So what you do, you simply, I have still 1 minute, so I'll finish by 1 minute. So this we look at this final map. So you want to take this s minus a to 0. So you simply compose with t s minus a. Okay. So if you compose with this, so you still have this will be slightly, kind of, now it will contain 0, but I have kind of bigger. So 0 now is here. So my f, this is composition of all this map f. There are too many, but they're easy to handle. Okay, so this automorphisms you can they're easy to handle, and then you have the square root, and then you have again t of s minus a. This is certainly taking all the steps are injective functions, so this is certainly injective, and then f injective, right? And z naught is also going to 0, so therefore f is our family f. So here is a simple exercise to show that f prime at z dot, okay, so is strictly bigger than the starting function f prime at z naught. This you see, you can differentiate this this automorphism TAs explicitly. Okay, it's simple calculus. You can differentiate, and if you do the computation, you use the chain rule. You will see that you get something bigger. Okay, so this will give you a contradiction, right? Because small f had had the maximum derivative, but I have produced now a capital F in the family with more derivative. So that contradicts our assumption that f is not surjective. So this completes the second step. So in other words, we have a now conformal map from the domain D to the unit D. So this completes the proof, okay, due to Carathéodory. Okay, so this is more about, so all about the history and the standard proof. Develop a method for solving the Dirichlet problem, and finally, by next week we will definitely try to learn the proof along the lines of Riemann. Okay, so I think I will stop here. Thank you.
Thank you, sir. Thank you for the nice talk. So if participants have any doubt, they can raise hand so that we can call one by one. Nirmal?
Hello.
Yeah.
Sir, you said that we will use Kobe's theorem and Carathéodory method to prove a Riemann's theorem, but we didn't use
No. I didn't say Kobe's theorem. I said Kobe simplified this Carathéodory's theorem. Actually, Carathéodory's theorem, yeah. So that's what I mean. Not Kobe's theorem, but Kobe simplified this. The version that we are seeing is, simplification by Kobe. Yeah.
Okay. So one more question: is there any another proof of Riemann mapping theorem which actually use the Kobe's theorem?
No. I, to the best of my knowledge, I don't know. Yeah, I don't I don't think it's it is there. Yeah.
Okay. Thank you.
Akash?
Hello. Sir, can you please go back to step 1?
Step 1, okay.
That side. Sir, the fifth slide. Yeah, sir, in the end, we have to prove this family is non-empty.
Yeah.
So that F we got, that is enough now. We don't need to compose it with TP, right?
No, see, this condition was also there in the family that I want to map So where did I define this family? Yeah, here. So this is another condition that Z0 should be mapped to 0. So what I produced is that a map that goes to the unit disk, but to make sure that Z0 goes to 0, so you have to compose with this. Oh, sorry, here so this was not the unit disk, this was the domain D. Okay. So this will, so after composing with this map, so whatever requirement you need, so it will go to Z0 to 0. So that's what is needed. Okay, so that it's a member of the family. Yeah. Yes, Akash.
Yes, sir. And sir,
Oh,
in
you.
proof where you wrote for any domain, we can find a unit disk in the complement.
You can find some disk in the complement, not any disk. Yeah.
What if we take our domain to be complex plane minus negative real?
You can see this method still works. You take square root, it will kind of expand the. See here, my picture. You see, if the blue line is kind of it's a curve, is missing. You can take positive real or negative real, doesn't matter. Any curve like this, you are omitting. So any simply connected domain. This is just a for the picture only. I'm taking this thing, but whatever I have written on the right side, that is for any simply connected domain, and A is on the complement, and I'm trying to enlarge the or widen the complement so that there if this actually fits inside. So the calculation in the right hand side is for a general simply connected domain. The picture on the left is something for it is kind of intuitive. Yeah. It did, yes.
Sir, can you please tell me again that's why we only working on the real part, sir, not on imaginary part of function, sir? In first slide, sir.
Oh, okay. So the Riemann's idea, right?
Yes, sir.
Yes, because if you know the real part, you can actually determine up to some constant the imaginary part also, right? Because you are working on a simply connected domain. So where is this? So given a harmonic function, I can up to constant, I can determine their conjugates, right?
Yes, sir.
Yeah, that's what I mean. So if you find U, there will be, you can find B up to some constant. But with all these equations and all, possibly you can write down what should be the correct B. Okay. Yeah.
Anyone else?
Yeah. Can we have a group photo if it's all right?
Yeah, sure.
Okay. If there are no more questions, of course. Anyone has any other question? You can ask now.
Just one question.
Yeah.
Is it easy to see that? I mean, as a corollary, it will follow that any simply connected domain will be, which is proper, and it will be homeomorphic to unit disk. But is it? I mean, easy to see that fact without using this Riemann mapping.
Homeomorphism.
Yeah.
See, there are certain results, of course, but yeah, I don't know it well.
Yeah. I mean, even that seems to be an interesting. Consequence of this. Yeah.
Yes, but definitely there are results. Yeah.
Okay. Thanks. Yeah.
Sir, hello.
Yeah.
So the HZ you are considering here, is it unique for G is equals to e to the power Z, e to the power HZ?
No. See, this uniqueness and all, this is kind of, we're walking kind of backward. Okay. We're trying to, so if there is a biholomorphism, we are trying to understand how it has to look like. And then the idea is to walk backward. You're trying to find an equation and, in F, and then you try to, walk backward to solve this and get a solution. So this is only a sketch of what Riemann was doing. How to, try to in fact come up with something like this F. Okay, so this is, so all these things has to be, sorted out after you find some U, even if there is a U like this, and then you have to work it out that the resulting function F is say bisective and all these things. Yeah.
But Diganto, I think the holomorphic logarithm, that part, up to multiple of, that more or less, up to 2 pi I, integer multiple of 2 pi I. Up to that, it should be unique because of
Right. Yeah, correct. Yeah, up to some constants. Yes.
Yeah. Up to.
Yeah, if there is no other doubts, let's thank Professor Borah once again for the nice talk. And I also thank the participants for the active participation. Now, our next talk will be on tomorrow, 3 p.m. The Zoom ID will be the same. I hope everyone will attend that. Now, if everyone is okay, they can turn the camera on so that we can take a group photo.
So let me stop sharing the screen so that, right.
Yeah, all of you kindly open your videos if you'd like yourself to be in the photo. Yeah, some more. Yeah, please. Okay, so on the count of 3, maybe we'll have some photos. Ready? 1, 2, 3. One more. 1, 2. Yeah, thank you. Let me stop the recording.